Hello and welcome to our next lecture on Unit 6 about the atmosphere. This unit is a little dense in the context of what you're reading for how long the chapter is and kind of some of the complexity of it, but I really wanted to simplify things. So I hope that's what we're going to accomplish here. That's my goal, to make this a little bit easier for you guys to understand without getting kind of overwhelmed. The atmosphere is a big deal, you know. I mean, it really is contributing to a lot of what goes on with our well, it's everything above the earth, right? So our weather and our climates and clouds and rain, you name it. The atmosphere plays a role in some regard with all of these things. So um, it's a very important piece, and it kind of brings us into opening up the, let's call it, 6 week or so discussion of where we talk all things related to what's going on above the surface of the earth. So look forward to that over that kind of time period as we kind of break down and get more detail each week. This is the overall, like I said, for the atmosphere, which is the whole thing. But now we're going to start getting into, or after this lecture, we're going to start getting into individual kind of pieces and get down to the details. So let's begin talking about the atmosphere. And first and foremost, let's designate the difference between two very important terms that we use in everyday common language and the way we talk. But it is important to distinguish these things in a certain way. So when we say weather, when we use the word weather, we're talking about short-term conditions, short-term conditions of something going on in the atmosphere, as opposed to climate being long-term conditions of weather over a region. Basically, what we're saying is weather is, if we're comparing the two things, the differences between the two, biggest one, weather would be things that happen on a daily basis, maybe weekly basis at the most. What's the weather for this week? But once you go kind of beyond that, things become more predictable. And once it becomes predictable, it becomes the climate. So, like if it's hot for a period of 3 months, say for example, then it's more kind of predictable that it's going to be like that every year. That's going to be the climate. Whereas if it's hot today but cold tomorrow, well, the weather is hot today but the weather is cold tomorrow, right? Something along those lines. Restless atmosphere conditions, that means, you know, things like uh, the atmosphere is so in other words, things like there are thunderstorms. A thunderstorm is happening within a couple hours, and uh, then after that everything dries up, right? So that's what we call a restless or an unstable atmosphere. And weather is, when we say the weather, we're referring to these kind of whether it's whether it is um, minute by minute, hour by hour, week by week, and so on, something along those lines. Okay, so it's important to distinguish the difference between those two things. And moving on, we do have to talk about what is in the atmosphere. I want you guys to certainly know these things, and I don't really throw a ton of numbers at you guys because that can just become like, honestly, not super relevant or important. Uh, but when it comes to numbers, I definitely want you guys to know these specific percentages, and you know, kind of keep these in your memory bank. Okay, so this term first let's just describe this thing called constant gas. Okay, three most constant gases. A constant gas is something in the atmosphere where it's basically always there, constant, like it doesn't really change. Okay, that's what we mean when we say constant gas. So some type of, excuse me, molecule in the atmosphere that's kind of basically, it never goes away. And so 99.9%, it's like the entire atmosphere let's say, is made up of three major constant gases. Okay, three main constant gases. Okay, first one is nitrogen, or N2, and nitrogen makes up, get this, okay, 78% of the atmosphere. 78% of the atmosphere. So that's more than 3/4 of the atmosphere is made up of nitrogen. And the reason that nitrogen is such a constant gas and is always there is that it does not react easily. So in other words, it doesn't really mix well or kind of break down when it comes in contact with other gases. And basically, in that case, then it just dominates the atmosphere and it never goes away, in a sense, right? So definitely remember that nitrogen is the big one. That's what takes up the majority of our atmosphere there. Oxygen would be the next big one, okay? And oxygen is extremely abundant in and around us. O2, oxygen makes up 21%. So just look at that, 78 and 21. We're almost at 100, almost, really. But yeah, oxygen's a big deal. So for oxygen, when it comes to why it's so important, I mean, I think it's pretty obvious, right? But when it comes to, for animals, oxygen, it burns food. It creates energy. When oxygen is burned, it creates energy. Okay, this whole process is known as oxidation. Sorry, oxidation. This idea of oxygen creating energy. Okay, so when you burn what's known as fossil fuels, things like gas and whoops, not right now. Restart tonight. Okay. When you burn things like gasoline or oil or gas, natural gas, etc., that is a form. There's a process of rapid oxidization going on. Burning oxygen, in a sense, in those contexts, especially like an internal combustion engine. You've got oxygen and gas kind of mixing together. Boom, now you've got rapid oxidization. And where do you get the energy from? That spark, okay, or that spark kind of creates this energy, and boom, now you've got your engine moving and your car drives, right? That's the idea. So yeah, this process of oxidization, it's balanced out by photosynthesis, which is plants using carbon dioxide as food and then reproducing oxygen, right? So plants give off oxygen. It's like the opposite of humans. We consume oxygen, but we release carbon dioxide, whereas plants eat carbon dioxide and release oxygen. That's, I know I'm being very general and as I'm saying this, so if you're a person that's into plants, don't destroy me on this, but basically what I'm trying to say is that's photosynthesis in a nutshell. It's the process of plants eating and then releasing oxygen as their that's their byproduct. So that's a good thing, in terms of like kind of keeping the environment in check, because if we don't have plants on Earth, then we're not going to have oxygen as abundant as it needs to be to keep life going. Okay. Cool. All right. So moving on. The next one is argon, and it is let's just call it slightly less than 1%. And you might go, why the heck is that even on the chart? Well, if you notice, 78 plus 21 equals 99. So the next biggest number in there is a little bit less than 1%, and that's argon. So we're left with very small percentage of everything else in the atmosphere. Okay, but yeah, just because it is close to that 1%, we throw it into the big three, even though it's obviously a much smaller percentage compared to nitrogen and oxygen. Okay. Let's see. So yeah, individual molecules come and go in the atmosphere, but the number of overall molecules is constant as long as the gains equal the losses. Okay, so that's not to say that all nitrogen and all oxygen is forever. And all argon is forever. I mean, certainly it can be broken down or lost or things like this nature. But the fact that these gases are replenished in one form or another, that's what we mean by the losses. The gains equal the losses, right? So there's as much going out as there is, or there's much coming in, or there is as much going out, kind of thing. That's what the idea is, and that's reigns relatively true when it comes to these constant gases. Okay, keeping them constant. Let's see. So when it comes to we talked about, we've got constant gases which make up the majority of the atmosphere, right? That 99.9%. And then when it comes to everything else, which you might say, well, that's not very significant, but it is, because that 0.1% is extremely important because we've got such a variation of different molecules that make up, and strong molecules in that sense too, that make up the rest of the atmosphere there. So we define how much molecules of gas exist in the atmosphere by its fraction of a million. Okay. We're calling these small amounts of gases, small amounts of molecules, we call these things trace gases. Okay, so I'm jumping down here for a minute, but because they're such a small percentage in the atmosphere compared to, the big three, we call them trace. Like there's little bits of them here and there. Okay, and so for example, like I said, we're trying to establish the percentage. How the number is too small to put it in a percentage, but if we break it down in a fraction compared to a million, that's the most that's the easiest way to really understand how much of this trace gas actually exists. And again, overall, sure, it's not a lot, but say 100 parts per million versus say 900 parts per million, that's a very significant difference in those two gases. And if it's something like carbon dioxide, or smoke in the air, or dust, or something like that, I mean, that's a significant change to what the atmosphere smells like, feels like, looks like, right? Acts, etc. Okay, so that's an important thing, and I really want you guys to grasp and understand what this parts per million thing means. To abbreviate that, we say ppm. So for example, carbon dioxide, okay, CO2. CO2 could be somewhere between 400 parts per million, and we would shorthand write that 400 ppm. Okay, so that means that there are 400 CO2 molecules for every 1 million molecules overall, samples in the atmosphere. Okay, so it doesn't sound like a lot, but again, that's we'll find out more why CO2 is so important, but that's kind of neither here nor there at this particular moment in time. You saw a little bit in the last section video how it's a greenhouse gas. So kind of keep that bookmarked in your brain for now, and we'll get more into it. What I'm trying to get across to you guys is this idea of the numbers in this sense, and the ppm, what that really means. Yeah, so we know these trace gases, there's not a lot of them in comparison. And the other thing too is that they don't last that long in the atmosphere, right? They just don't exist a long time because they can break down very easily, and they can mix with other gases very easily. Compared to, when I say these things, I'm always kind of comparing now to the constant gases. So this idea of how long a molecule will remain in the atmosphere, it's called its residence time. Okay, essentially, think of it like its lifespan for a molecule, right? Is it gonna live in the atmosphere for a day, for a week, for a month, for 10 years? That's its residence time. Okay, and let's move down here. So yeah, another major bullet point is talking about the atmosphere. And so let's kind of take a trip back in history, talking about the atmosphere in early days of Earth, not man, but Earth itself, right? So way, way, way before human beings were inhabiting Earth. And the early atmosphere consisted mostly of water vapor, okay? Um, and it was very void, meaning that there was hardly any oxygen in the atmosphere at all. And so, without oxygen, well, it was not very habitable for animals. That's the idea. So, and we're talking billions and billions of years now, right? Billions of years ago, and billions of years to kind of progress or evolve. And over that time frame, oxygen increased in the atmosphere, and the way it increased was once vegetation, so plants, okay, once vegetation started to evolve on Earth, and now we're actually down into millions of years ago, okay. So vegetation, well, what do we know? Plants give off oxygen. And so the more plants, the more oxygen. And so that's kind of how we got to where we are today. And that's not to say that within our lifetime or even our kids or grandkids' lifetime that this you know major shift in the amount of molecules is going to change, because we know that oxygen is very constant gas. But say over the next millions of years, we could see something like this again, another shift. Don't know. Could be a different form where oxygen goes away and maybe it's some other carbon molecule. We don't know. But yeah, that's what things were like in terms of the atmosphere in the early time of Earth. Okay. um, okay, so we talked about gases present in small amounts are called trace gases. Um, variable gases, okay, gases present in varying quantities. Um, so variable gas and trace gas is kind of similar, except variable is harder to let's say, well, variable is going to, um, there's certainly a lot less of it compared to constant, but your variable is going to really vary a lot in its quantity. So that is very similar to trace gas. I understand this. Um, let's kind of break down some of the major ones that I want you to know in terms of this variable gas, okay? And we come back to carbon dioxide here, CO2, okay? The reason why CO2 is so important is because CO2 can absorb, okay, and emit long wave radiation, right? So we saw that at the end of chapter 5, the video with the little pinball thing, and the more CO2 greenhouse type gases there were, the more it kind of trapped that that radiation. So in a sense, that creates more of that radiation to stay in, closer to the Earth. Again, long wave radiation, right? Let's see. So the majority of Earth's carbon, okay, it's stored in rocks, okay, in the ocean. So carbon dioxide is not just above the Earth. It's actually in many other places, whether living or non-living things or beings. And yeah, it's stored in rocks. And so what's really interesting is that scientists can observe, and we'll learn this with climate change because there's a connection there. scientists can connect variations in temperature on the Earth, variations in climate on the Earth, with the amount of carbon dioxide that has been on the Earth. And so, if you've got carbon dioxide stored in rocks that, let's say, scientists understand the rocks are X million number of years old, well, then that's kind of an indicator of how much carbon dioxide, more or less, was in the atmosphere at that time. Okay. And so, kind of looking at that, these correlations exist, and we'll definitely get kind of bit more into that once we get to those units. But it's kind of interesting, so much of this is stored in the earth, stored in the rocks, in the dirt, under the ocean, in trees, those type of things. Okay. Um, let's see. So, it's a kind of an important thing, because let's say when a forest gets cut down, um, two things kind of in a negative sense happen. First would be that you lose the plant giving off oxygen, right? That's not going to exist anymore because the plant's dead. So there's no more oxygen being given out. At the same time, as the plant is decaying, carbon dioxide is being released. Okay, so it's, I guess it depends on the way you look at it. You could say, well, it's more food for the other plants, which is sort of true. But at the same point, if you don't balance that out somehow, then if you don't have more plants, more trees planted in that forest, then you kind of lose that balance, or you gain a new equilibrium, similar to what we talked about with the thermal equilibrium thing, right? This is a similar type of idea, just different context. Okay, another important one we mentioned a moment ago, but water vapor. Now, when I say water vapor, I don't mean like just raindrops, right? Sometimes the water vapor is so small, such a trace gas, and such varying quantities, as it is a variable gas, that you can't even see it, right? But it's still there. Anywhere you look around you, there's some type of water vapor around you, right? That's how you end up with humidity, okay? And we will explain more of that too once we get into water vapor discussion in the air, in the atmosphere. There's a whole unit on that, unit 11. But yeah, water vapor, it carries amounts of latent energy from place to place, which is essential to keep the Earth's temperature habitable. So we learned this before, right? This latent energy is another way of kind of saying this is, the more latent energy released, the warmer something is. Kind of like the idea of the ocean absorbing the radiation versus the land, emitting the radiation type of thing. And so this water vapor is carrying this energy from place to place, which kind of, as wind and currents, etc., flow from one part of the earth to the other, it kind of, as we mentioned, I think it was the quote in the last one, that the atmosphere was the number one reason why. It was the convection talk, right? And so this idea of flow, okay, so this is all related to convection heating. Okay, convection heating, the flow in the air when it comes to water vapor, that flow, kind of keeping things in a stable temperature, right? So even places like I mentioned, Europe, high latitudes similar to Canada, but because of the flow of air, you have warmer temperatures in much of Europe compared to parts of Canada, right? Simple examples like that. Oh, okay. So I kind of skipped over the residence time of CO2, which is less than a decade. Sounds like a long time, which is pretty significant amount of time compared when you consider what impact it has on the actual environment. And then water vapor, kind of completely on the other side of the spectrum, much smaller residence time. Less than 2 weeks. That's not to say that it's not significant either, but it's a much smaller time frame. Okay, water vapor is also a huge greenhouse gas when it comes to absorbing heat. Okay, again, how humid is it outside, right? When there's higher humidity, it feels warmer, right? It feels warmer. But we'll also talk about specifically why that is when we get to that section. Okay, when we get to that unit, which is down the road. Okay, now I also want you guys to know about ozone. Okay, ozone is an extremely important variable gas, and it is formed at the highest altitudes, and so really, far up in the atmosphere, um, and um, uh, and in tropical latitudes. Okay, um, let's see. Da, da, da. Important because ozone absorbs ultraviolet radiation, which is harmful. I'll just explain these bullet points and we'll watch this video, okay? So ozone, the molecule ozone, it absorbs um, the shortwave radiation called ultraviolet, which is at the very shortest end of the spectrum of shortest waves of the spectrum when it comes to what's released from from the sun. And so that stuff is extremely hot and harmful and can really burn you. Just your skin alone. It can, when we talk about sunburns, skin cancer, that type of stuff. Exposure to ultraviolet light, ultraviolet radiation, is a big deal, right? So we need ozone in the atmosphere. We definitely need it because it helps absorb that harmful stuff, right? Um, Now, I do want to say another thing here is that ozone. So you probably heard this term called ozone layer, which is like this big blanket over the Earth, okay, of ozone molecule. And this ozone layer, um, right? We understand why it's important, but there is a hole that exists in this layer, okay? And in this hole exists due to, it sounds like a strange thing, but this hole exists because of human behaviors using something called chlorofluorocarbons, okay? You could just say CFCs. And these CFCs, okay, we're going back to uh, like the 50s, 60s, 70s time frame, okay? And these were, this chlorofluorocarbon was a molecule used in solvents and air conditioner coolants. So things that would those type of chemicals and things that were used to clean you know heavy material, right? So um, again, it's like going back in time and saying, well, these are great products, but we don't know how harmful they are to the environment. um, and lo and behold, it was doing some pretty major harm because it was affecting this ozone layer, which if we didn't have that on Earth, we would probably not exist because we'd all burn up, right? But it did create a hole, which is a significant occurrence in time. Um, so yeah, I want you guys to know that for sure. And let's see. Let's watch the video and then I'll kind of move forward with the rest of this stuff. So here's the YouTube video. And let's see here. Oops, that's not the right one. Here it is. Okay, we're gonna watch this now.
15 to 35 kilometers above Earth's surface, a gas called ozone surrounds the planet. The ozone layer acts as a barrier between Earth and ultraviolet radiation from the sun. However, pollution has caused the ozone layer to thin, exposing life on Earth to dangerous radiation. Earth's atmosphere is made up of 6 layers. The second layer, called the stratosphere, contains the ozone layer. The ozone layer is made up of a highly reactive molecule called ozone, which contains 3 oxygen atoms. Ozone is a trace gas in the atmosphere. There are only about 3 molecules for every 10 million molecules of air. But it does a very important job. The ozone layer acts as Earth's sunscreen, absorbing about 98% of damaging ultraviolet or UV light. But the ozone layer has gotten thinner. Chemicals called chlorofluorocarbons, or CFCs, are the primary culprits in ozone layer breakdown. A CFC is a molecule that contains the elements carbon, chlorine, and fluorine. CFCs are mostly found in refrigerants, aerosols, and plastic products. When CFCs are exposed to ultraviolet rays in the atmosphere, they break down into substances that include chlorine. The chlorine reacts with the oxygen atoms in ozone and rips apart the ozone molecule. Areas of damage in the ozone layer are often called ozone holes, but that name is misleading. Ozone layer damage is more like a thin patch, with the thinnest areas near the poles. The ozone layer above the Antarctic, in particular, has been impacted by pollution since the mid-1980s. There, the region's low temperatures speed up the conversion of CFCs to ozone-damaging chlorine. About 90% of CFCs currently in the atmosphere were emitted by industrialized countries in the Northern Hemisphere. In 1989, the Montreal Protocol banned the production of ozone-depleting substances. Since then, the amount of chlorine and other ozone-depleting elements in the atmosphere have been falling. Scientists estimate that chlorine levels will return to their natural state in about 50 years. By then, the Antarctic ozone hole will shrink to smaller than 8 million square miles.
Yeah, so chlorine, that's the big one out of those CFC molecules that is, the most detrimental to the ozone, the oxygen, as it said. And the good thing is, as scientists are starting to see that things are turning around because CFCs really aren't used anymore based on this, because of this Montreal Protocol. Even though we still have Freon and other things to kind of power our, they're built in a different way or with different molecules that don't emit these CFC, byproduct. And that's a good thing. We're looking at, the mid 2000s, right? 2050, 2060, potentially that the biggest hole in the ozone layer where the where Antarctica is, could kind of repair itself or be completely repaired. Let's hope so. Okay, and then the other one here is methane. And methane is most effective at absorbing long-wave radiation. Yeah, methane's a bad stuff when it comes to adding too much of it to the atmosphere. And again, we're talking very, very small amounts in comparison. But again, we have to think about how much was there before human beings and before industrial activities of humans, and how much is there now. So it's like if you have something that was 10 and then it moves and it becomes 20 and then it becomes 40 and then it becomes, right? So as it's kind of exponentially multiplying, that's what's going on here. And you have these dramatic effects on the actual climate, even though these are small amounts of gas in the air. Methane comes from various sources, but things like fracking, and which is you know, extracting natural gas um, from the you know, subsurface of the earth, uh, animal flatulence. Believe it or not, cow. The more cows, this is going to sound like a funny thing, but the more cows there are, the more methane is going to exist. And so you kind of think about that too. It's like, well, so what if there's more cows, right? How do you end up with more cows? Well, cows are going to be something that are produced, right? I guess because of demand. You know, that's a business. Ranching is a business, and so the more uh, people there's going to be a demand for cows for consumption. Let's just call it what it is. And you know, all of these things you can draw down the line and really get into rabbit holes with this. But what I want you to know in this particular section about methane is this is pretty nasty stuff, right? In this context. um, let's see. The last point I want to make before I show the last video, the next video to kind of close this, is the term particulates. You may have heard this on the weather report before, but a particulate would be anything that's like any type of molecule that is suspended or kind of falling, okay? Um, like a falling liquid or some type of solid. So something like smoke, or dust, bacteria, fungus, you know, that type of stuff, especially during, you know, fall and spring, when there is like allergy reports, you know, you have pollen, these type of things. Um, they don't necessarily stay in the air, but they stay suspended long enough that it can affect, you know, the atmosphere. It can affect kind of locally an environment, and certainly can affect, you know, how people breathe and other things, etc. Right? So that would be that's what those type of things are called particulates. Okay. Um, let's put it down into a more general terminology. Particulates, the more particulates there are, the more air pollution there is. Okay, the more air pollution there is. So things like smoke and I mean, obviously that's from, say, fires, wildfires or burning fires, but any type of byproduct like that, right? Like burning gas and the emissions that come from the car, right? They're emitted and that becomes part of the air pollution. Well, those types of molecules, a lot of them become particulates in the air, right? And it's something that is observed much more prevalently in urban areas. Okay, well, there's a lot more air pollution in urban areas because there's a lot more human activity and a lot more of this type of. It kind of makes sense in that way, that you would have more of these particulates, particulate matter, particulate substances in the atmosphere. I think I skipped over a couple slides, so let me back up for a second and just make sure I cover these before we show the next thing here. CO2, let's go back to this, the idea of the 400 parts per million. Slide 15. Here we go. Okay, so yeah, this is when I was saying in relative terms. Take a look at this. We're talking about a span of about 50 years, and this is Manua Loa. I guess this is somewhere in the Pacific Islands. And just take a look at the increase in carbon dioxide over that 50-year period, which is a very, very small blip of time compared to the entire Earth's, you know, lifespan. But that's an increase. If you say 300 to 400, that's an increase of 33% in a very, very small amount of time, right? And so if this kind of continues, obviously the environment is going to be significantly impacted because one of these molecules that has greenhouse gas type molecules is exponentially increasing, right? That's the idea. And what else? So no clouds without water vapor. Okay. You know, water vapor can be defined in either like the gas, like the vapor, which you don't really see that stuff, or the liquid, or solid ice. You know, in that case, snow or rain, or just what's ever present in the atmosphere that is going to be around us that we don't necessarily see in terms of a gas. All right, that's all for that part. Now, these final three here, or these final five spheres, okay? Do not be, if I ask you on a quiz and I'm talking about something related to a sphere, be careful, because remember that there were the 5 spheres of the Earth, okay? Litho, hydro, cryo, atmos, and biosphere, right? Those are different than the spheres when I say the spheres of the atmosphere, okay? So again, make sure that you compartmentalize those two different things. So spheres of the Earth, the latter I mentioned. Spheres of the atmosphere, however, something different, okay? So you might see questions like this. You may even see in the same quiz where we talk about spheres on the Earth, spheres on the atmosphere. Do not repeat the answer in both places. I'm just telling you this now because it happens all the time. I wouldn't ask the same type of question 2 times in a quiz. That would be redundant. So don't give the exact same answer twice. This is like the best tip I can give you when it comes to, previewing what's going to happen on the quiz. Anyways, spheres of the atmosphere. These actually, there's only 4, right? 4. I thought it was 5 as I kind of glossed over this, but it's 4. Troposphere, stratosphere, mesosphere, thermosphere. What I want you to know with these, in terms of details, I want you to know kind of like where they exist. So it's like different layers in the atmosphere. Okay, here's one, here's the other, here's the other. Okay, like that. So the ranges in altitude, and I want you to know what happens to the temperature in these atmosphere spheres, okay? So I'm not going to read these because the video is going to describe it pretty detailed. And then that's going to be it. I'm going to go ahead and log off after that. So I won't see you again. Thanks for watching, and enjoy the rest of this video.